All right, welcome back. Here's midterm one for physiology. I must make a little disclaimer first before we begin. So I made this exam completely by myself, and this is something you would definitely see almost identical to a university level physiology exam. There's not really multiple choice questions like I give you a question, is this A, B, C, or D? Nothing like that. This is more like a university type exam, not like a high school. However, if you would like me to make something like multiple choice test, I'll be more than happy to do it. Just please leave in the comments. Please reach out to me. Also, if you really like what I'm doing here, please like and subscribe, but also share this video with your friends or students or whatever. I want this to get to as many people as possible so people can get A's and whatnot. I want this to really help people. That's why I'm doing this. So it did take me a long time to make this exam, but of course it's worth it. So let's begin. We have a cell membrane here. And we got the resting membrane potential of negative 40 millivolts. In the membrane, rather in the cell, we have ions X, Y, and Z, all negatively charged. Notice there's a negative sign here for all of them. And the respective reversal potential. Letter A. Which ion has the greatest amount of electromotive force? Prove your answer using a particular equation. Wink. So go ahead and try this out. Okay, so rotate the page. What's the equation we're talking about here? I did not mean to do that. Okay. Chill out, iPad. Okay. So we're talking about the force equation. Force equals resting membrane potential minus reversal potential for that ion. Okay. Let's do ion X. Force equals resting membrane potential, which is negative 40, right? Negative 40, minus 40, which is the reversal potential for X. This equals 0. Why? Force equals negative 40 minus like 105 because it's negatively charged. It's negative 105. This equals 65 millivolts. All right, let's do Z. Force equals negative 40 minus 55. It's positive, right? Positive 55. That's Z. This equals negative 95 millivolts. What's the correct answer? Be careful. You might say it's Y, which is 65 millivolts, because that is the highest number, right? If 0 compared to negative 95, 65 is the most, right? Wrong. So what you're looking for is the absolute value of these numbers. So the absolute value of 0 is just 0. Absolute value of 65 is 65. And the absolute value of negative 95 is positive 95. So technically 95 is the highest. Greatest electromotive force. So the answer right here is Z. If you open all the Z channels, circle what's going to happen. Okay, so if you open all the Z channels, so we're at negative 40, right? So pretend it's negative 40. And then the reversal potential of Z ion is 55 millivolts. We don't care what the other ions, because they're closed. We open all Z channel ions. Open all Z channels. X and Y, they're closed. Only the Z ones are open, so that's all we care about. We start at negative 40, and then we open everything up, and we go all the way to 55. That means we're going to depolarize because we're going higher. The voltage is going up, right? From negative 40 to 55, we went up. That's depolarization. Which direction are the ions going to move? The Z ions. Which way are they going to move? It's going to be an efflux. Why? Notice that, okay, we have our cell here, and we have Z ions. And then we have our channel here. No, we have a channel here. Okay. If we're going from negative 40 to positive 55, we're getting more positive. So that means Z ions, because they're negatively charged, are going to go outside the cell, meaning the cell will get more positive. Just imagine if the Z ions went inside. Z ions, right, Z ions are negatively charged. If you put more negative stuff inside the cell, it's going to get more negative. But if we take out negative stuff out, of the cell, like we're taking out Z ions, it's going outside. Z ions are negatively charged, right? But if we take them out, it's going to get more positive. The cell's going to get positive. That's what's an efflux. Okay? See, Keishan comes along and stabs this poor creature with a needle that contains a mysterious drug. Ooh. After careful observation, Keishan realizes that the drug blocked all the X ion channels in this poor creature. The membrane potential did not change. What can be said about the ion's permeability to the membrane? Mention ions X, Y, and Z in your answer. Okay. We said that we blocked all the X ion channels and the membrane did not change. So let's talk about X first. If the membrane permeability did not change, well, first, let's see that what it is. So we have negative 40 is the reversal potential for X, and the resting membrane potential is negative 40. They're the same numbers. So if we block X and the membrane potential doesn't change, the resting membrane potential doesn't change, X has no effect to resting membrane potential. If it had some effect, well, then the resting membrane potential would have been different. Okay, let's talk about Y. Okay, Y has to do something. This right here is a certain fact right here. This is certain. It has no effect. Y has an effect. Has an effect. Z also has an effect. I'm describing both of them at the same time on purpose. Has an effect. Rather, it is permeable. It is permeable. And this would be like not permeable. Sorry about that. Okay, Y. So X is not permeable. We can already say X is not permeable. Does not matter. This does not matter. If Y was not permeable, so pretend Y was not permeable at all. That means the only thing that's permeable is Z, which is positive 55. This needs to match with this, but it doesn't. Okay, so this means that Y must be permeable. Okay, at least it must be permeable. So let's say this is permeable. Okay, now pretend this was not permeable and only Y was. This still doesn't match, right? Negative 105 does not match negative 40. If that's the only ion that's permeable, this means this has to create the resting membrane potential. That's the only ion involved. But it's not. So basically what I'm saying is that ion Z is sharing some of the responsibility to create the resting membrane potential. Sorry about that. So it's these two ions in combination that's causing us to have a negative 40 millivolt resting membrane potential. The mixture of positive 55 millivolts and negative 105 millivolts. It's basically the tug of war between these two reversal potentials is causing the resting membrane potential to be negative 40 millivolts. Sorry about that. All right. 2, we have the super awesome picture above shows a normal, healthy action potential. Keishan, being a menace he is, takes a needle and injects a drug that makes all potassium channels open at the exact same time in voltage as the sodium channels. Draw the new action potential graph. Okay, in one of my videos, the potassium channel video, I believe, I said the potassium channels open at a later time than the sodium channels. They're slower to open and slower to close. That's why we get this normal looking action potential graph. Now let's see if they open at the same time. If sodium channels open and potassium channels open at the exact same time, at the same voltage, what would it look like? Well, let's draw our little graph here. If they open at the exact same time, well, it's going to be a flat line. Because no matter what the voltage is, right? So they just say it is negative 45, for example. The same amount of ions, right? The same amount of ions with potassium, and say you have sodium. The same amount of ions, the same amount of sodium ions is going to enter the cell as the same amount of potassium ions are going to exit the cell. Because this is a potassium channel, this is a sodium channel. Same voltage, same time, same amount of ions. So it's literally like we took out 3 potassium ions and we put them outside, but to replace it, we just put 3 sodium ions inside. So nothing really happened. It's just they just switched places. So it's going to be a flat line. Okay. You're probably thinking, damn, Keishan has a lot of mysterious drugs. You'll be correct, because now he decides to inject a drug that blocks all sodium channels and opens all potassium channels. Uh-oh. Draw the new action potential graph. The reversal potential of potassium is negative 80 millivolts. Okay. No sodium in this that's going on here. So we basically start out normal, and then we're going to dip down, say this negative 80 millivolts, and this like negative 65. Okay. We're going to dip down, and it's going to stay here. Because remember, potassium is the only ion that matters now. And it has a reversal of negative 80 millivolts. That means that's basically going to be the new resting membrane potential, because that's the only ion involved. Okay? Using the scenario from above, are we depolarizing or hyperpolarizing? What about the direction of potassium ions? Okay, we are hyperpolarizing because we're going lower in voltage. Lower in voltage means hyperpolarizing, not depolarizing. If you were getting higher in voltage, we'd be depolarizing. What about the direction of potassium ions? What do you think? Potassium ions are going to go outwards. Outwards. Right. Why? Well, like I said, we in the previous example here, the potassium ions. Potassium ions are positively charged. We're at negative 65 and we need to go to negative 80. So we need to release some of this positive charge, right? So it gets the membrane, the cell becomes more negative. Okay? So potassium ions are going to go out the cell. Potassium is positively charged. If we take positive stuff and throw it outside, well, now we're more negative. Hope that makes sense. 3. Now on to some neuromuscular junction stuff. Answer the following questions. Treat each question individually. Circle the correct answer. You're comparing to a normal functioning neuromuscular junction model. So if we have a scenario, action potential does not arrive to the axon terminal, what's going to happen to the calcium inside the cell? What are going to be the levels? Increased levels, no change, or decrease? The answer is decrease. If the action potential just never arrives to the axon terminal, the voltage-gated calcium channels will never open up. So calcium, there's not going to be really any calcium inside the axon terminal. Action potentials on the muscle cell are going to be increased, no change, or decrease. We're going to decrease. We have no exocytosis of acetylcholine. So there's no acetylcholine that can actually bind to the muscle cell. If nothing binds to the muscle cell, we're not going to get any action potentials. Decrease. Okay, what about the status or the state of the voltage-gated sodium channels in the muscle cell? Are they going to be open or are they going to be closed? What do you think? Or don't know. That's an option. Closed. If there's no, like I just said, we got no calcium, no exocytosis of acetylcholine, nothing binding to the nicotinic receptors, the sodium channels are going to be closed because they open when something binds to the receptors, to the nicotinic receptors. That's how they open up. But if nothing is binding to those receptors, they're going to stay closed. Isn't this fun? Yeah. B. You injected a drug that caused all nicotinic receptors to be internalized. They aren't present on the muscle surface. What's going to happen to the acetylcholine production? Increase, no change, or decrease? No change. Everything's fine in the synaptic, in the neuron. We still got an action potential. We still got calcium coming in. We got exocytosis of acetylcholine. The mitochondria's working fine. Everything's fine. Acetylcholine present in the synaptic cleft is going to be increased, no change, or decrease? It's going to be increased. Okay, so there's no receptors on the muscle cell, correct? We're still exocytosing acetylcholine into the synaptic cleft. That's true. But nothing is going to be bound to the receptors because there's no receptors. So there's going to be more floating around in the synaptic cleft. That's why it's increased. But what about the amount of vesicles, the acetylcholine vesicles? Increased, no change, or decreased? No change. We're still making the same amount of acetylcholine. That's not going to change. Last question. I will make this a simple one. Keishan decided to go into the kitchen to make himself dinner. He started to boil some water. After some time, he comes back to check on the water. Keishan, being the smart man he is, burns himself by touching the metal handle. In response, he moves his hand away. Write out the entire pathway of sensory and motor information. Include what lobes of the brain were involved in this unfortunate scenario. Use words like afferent and efferent. Okay. So you got my hand here. I'm going to butcher this. Oh, dear. Okay. Oh, no. I do not have a big thumb. Hand. Problem solved. Okay. This senses, right? So say we have a fire here. Ooh, that's fire. Okay. Pretend. And I hurt myself. And I sense that, correct? So it's going to be a sensory neuron. We sense what has happened. You sense it. So basically sensory neuron, I should say. Okay. It's going to enter, or afferent, which is enter, the dorsal side of the spinal cord, or dorsal root of spinal cord. Okay, then we go to the brain. Then it becomes a motor neuron. Don't worry, I didn't forget the lobes. It becomes a motor neuron. Then we're gonna enter the spinal cord, and we're spinal cord. And then we're gonna exit or efferent, the ventral root of the spinal cord, SC for spinal cord. And then we're gonna move hand. Okay. What were the lobes? Okay, so we felt something, so we sensed something, and we moved something. So that's gonna be the parietal lobe and the frontal lobe. Watch my last video if you need help with that one. Okay, bonus. What types of receptors detected the stimulus in the first place? More specific than sensory receptors. Hint, it hurt and it was hot. I did. Okay. It hurts. Okay. Pain receptors are called nociceptors. Those are pain receptors. Temperature receptors are called thermoreceptors, as in temperature. And this concludes midterm 1. I hope you found this helpful. Please like and subscribe. And if you really like this, then I'll continue doing it. But please let me know. And please share this with your classmates or students or the world. All right, see you later.